some stream functions and all, and then we'll go to the actual topic. Okay. See, from the basic of our fluid mechanics, first of all we will recall what is required for this today's class. Stream function. Okay, I will not go into the much detail because it's a revision class. So, what are the stream functions? You see, a stream function is a function like if you want to know the velocity in x direction, okay, x direction, y direction, there is a flow, right? And I want to know the velocity of the flow in x direction, then it will be equals to delta psi by delta y. Okay. Similarly, the velocity in y direction, if you want to know, then that will be equals to minus of del psi by del x. Okay. This is for a Cartesian coordinate. If you want to express the same thing in a radial coordinate, if you consider the flow is like this, radial, the radial variation of the flow, and this is the radial variation and this is the tangential variation of the flow. In that, you can write the radial velocities as del psi by r del theta and tangential velocity as minus of dou psi by delta r. Okay. So, if stream function is known to us, we can determine the velocities. Okay, and stream functions we know that exist for the 2D flow only. Okay, two-dimensional flow only. So, if I know the stream function for a two-dimensional flow, then I will be in the position to say that what will be the velocity in x direction and what is the velocity in y direction if we are dealing with the Cartesian coordinate, and if you are dealing in a cylindrical coordinate system, then we will be able to tell what is the radial velocity and what is the tangential velocity. Fine. Then there is something called velocity potential, or you can tell potential function. Represented by phi. Okay. Potential function, if you partially derivate it with respect to x, you will get the velocity in direction of x. Similarly, if you partially derivate this phi with respect to y, you will get the velocity in y direction, and partial differentiation of phi with respect to z will give you the velocity in z direction. If you see the velocity vector, you can write it as dou phi by del xi plus dou phi by del yj plus dou phi by del z k. Right. You can write the same expression as my velocity vector is equals to gradient of phi. Fine. We have already studied vector calculus. In that I have told how to determine the gradient, what is the gradient. So, the gradient of your potential function gives the velocity vector. Okay, velocity vectors will have three components: the velocity in x direction, the velocity in y direction, and velocity in z direction, represented by w. Fine. So, this was our stream function and potential function. This is very important. Okay. Next, there is one more term that we will use in the revision, is the pressure coefficient. Right. See, the pressure coefficient is represented by Cp, and this Cp is given as P minus P infinity divided by Q infinity. Right. Here, P infinity is free stream pressure. Right. Q infinity is the dynamic pressure. not the, okay, dynamic pressure of free stream. You see, let us consider a ball. Okay, this is a ball kept in some type of flow. Let's say this is a uniform flow. Now, if you see the flow over this ball, this will be something like this, depending on the type of flow. It's a rotating or non-rotating cylindrical flow. Now, there will be some pressure here, P infinity. Okay, there will be some dynamic pressure of the free stream. The dynamic pressure is what you know, at half rho P infinity square. This is the dynamic pressure of the free stream. Then, if you want to know what is the pressure at this point, how can we tell? This Cp will help us there. If you will rearrange this term, you can write this as pressure at any point. Let's say if you are interested to find the pressure at this point, will be equal to free stream pressure plus Cp into Q infinity. If I know what is this value of Cp at this point, I will be able to tell what will be the value of pressure at that point. So, roughly you can tell this Cp is the indication of pressure at a particular point. Is it okay? It relates, Cp actually relates the pressure at that point with respect to free stream pressure. Correct? You can easily observe this expression. You just see this expression. P is what? Pressure at any point. Point on the ball. Let's say here we are considering ball. Pressure at any point on this ball will be equals to free stream pressure. This is a static pressure, right? Free stream static pressure plus Cp into free stream dynamic pressure. Is it correct? So, if I know the value of Cp, okay, then we will be able to tell the pressure at any point on the ball. Correct? Is it clear to everybody?
Yes, sir.
Okay. So, you can consider, let's say there is a wind tunnel. We are observing a ball in wind tunnel. You know the free stream pressure. You know the free stream pressure. That you know the velocity of the flow. So you can tell Q infinity. You know the P. Okay, and you know the Cp. So you will be able to tell the pressure at this point, this point, this point. Any point you can tell. Fine. So that is the importance of pressure coefficient. This will give us the drag and lift produced for a body in the flow. Then we'll go on the flows, types of flow. First of all, there is called uniform flow. Right. This is an example of uniform flow. Uniform flow may exist in x direction also, and it can be in y direction also. Okay. But for a general flow, you can represent the velocity. I am skipping the steps because it's a revision. You can represent the velocity in x direction as v infinity cos theta. Okay, and in y direction you can represent as v infinity sin theta minus v infinity sin theta. Okay. Similarly, for a source flow, this is a representation of source flow diagram. Of this, let's say this source flow has a strength of q. Then the velocity at, this is the origin, velocity at any radius r will be given as Vr, that will be equals to q by 2 pi r. Okay, what is the meaning of this? If I know the strength of my source flow, I will be able to tell what is the radial velocity at this point. Okay, lying at a distance of r from the origin. And for this flow, tangential velocity is 0. Okay, uniform flow completed, source flow velocity completed. Similarly, opposite, if you want to write for the sink flow, the sink flow is something like this, right? That means just you change the sign of q because it's a sink. So q by 2 pi r v theta will be equals to 0. There is no velocity in radial in the tangential direction. Only velocity component is in the radial direction. Fine. So these are three basics flow. Then, but in gate examination they will not ask this such simple flow. Okay, they will give you a combination of flow. Okay, and you have to write the velocity in the direction of x, y, and z. Okay, mostly you will get 2D problems. So in the direction of x and in direction of y. Okay, what is the velocity? So such one more case is there. That is the vortex flow. Right, just like source flow, in vortex flow also, if you see a vortex flow is something like this. You are moving in a this kind of circular path, right? So here you are having v theta, but the radial velocity is 0. In this case, you are having 0 radial velocity, and v theta is given as tau by 2 pi r, where tau is the strength of vortex. Tau is the strength of vortex. This 2 looks like same only, except in place of q I have put tau, or you can tell sigma. Fine, here q is the strength of source, and this is the strength of vortex. So both flows are same only. Here v theta was 0, here vr is 0. Fine. Now we'll go using this type of velocities. These velocities, I will generate the velocity component for different types of flow. Fine. So before going into that, I will like to summarize it here. We have seen first one, the uniform flow. Right, I will make a table. In uniform flow, I have seen the ux, or u is x only, no need to write x, is given as v infinity cos theta. Okay, and velocity in y direction is given as v infinity sin theta, minus of v infinity sin theta. Right, second type of flow, what I have seen, we have seen second flow. What is second flow? What I have is source flow. Okay, source flow, we are having radial velocity. At radial velocity, let me draw a line here. Right, the radial velocity is given as q by 2 pi r, and v theta is 0. Fine. Now similarly, third type of flow, is sink flow. What I told in sink flow, just you take minus q by 2 pi r v theta is equals to 0 for this. Similarly, the next one what I have seen is the fourth one was the vortex flow, right? Vortex flow was radial velocity for vortex flow was 0 and the tangential velocity was given by tau by 2 pi r. Correct? Source flow I have indicated like this. Sink flow I have indicated like this. Right? And the vortex flow I have indicated something like this. These are circles. Strength of tau, this has a strength of q, this has a strength of minus q. And for uniform flow, you can consider that my free stream flow is like this, v infinity. So that we are having, if this is my x direction and this is my y direction, you can, if this is theta, then you can write the x component as v infinity, cos theta, and this component as v infinity sin theta, y component as v infinity sin theta. Is it clear? We have summarized the type of flow, basic flow. And, and if you will see that I will be using this flow only. Most of the flow that is asked in GATE are the combination of this flow only. Fine. Now we will consider the first type of flow, that is Rankine half body flow. No, I have left one thing. I'm sorry. That is the doublet flow. Actually, it's a combination of flow. It's not a basic flow. So first of all, we will see the doublet flow. Right. See, what is doublet flow? We are having a source q and a sink represented by minus q of a strength q and minus q are at a distance of L. Okay. Now they are separated by a distance L. Then in every type of flow, we will be asked to find out the velocity at a given point P. Right. To determine the velocity at this point P, okay, we have to consider the velocity induced at that point due to this flow, right? And the velocity induced at this point by this flow. Okay. And the resultant will be the velocity induced at this point. So to determine that, we have to first of all write the stream function. The stream functions for a doublet flow is given by q by 2 pi theta, and for minus q it was given as minus q by 2 pi theta. Right. I will not go into the derivation part of it. Okay, in usual course I go in the derivation, but this is a revision, so I will write the final expression directly. If you solve it, you will get psi is equals to, that the stream function is equals to minus of k sin theta divided by 2 pi r. Okay. Now this you have to remember for the doublet flow. Fine. Actually, this also is not required. So remembering this also is not required. That we will see later. Why I am telling that is not required. Now, let's go for our first basic flow. First basic flow is what I told. The first basic flow I will see is the
uniform flow.
No. Okay, that is a basic flow. I will go to combination of flow now. That is
Okay, sir.
Rankine.
It's combination of uniform,
Uh,
source, and sink.
not sink. Rankine half body.
Okay, Rankine of body, source and uniform flow.
Yes, correct. Now I will tell you how I will use these velocity components. You see, we are having a uniform flow plus you are having a source flow, right? It then it will give you a Rankine half body flow, which is something like this. The diagram is not that good. Okay, you see, basically what we will do now, we'll to get this type of flow, what we'll do, there will be some string function for a uniform flow. There will be a string function for a this source flow, and the result addition of these two will give us the uh, string function for Rankine half body. Okay, but what I will do, I am interested in what I am having a 2D flow. I am interested in knowing what will be the radial velocity and what will be the tangential velocity. Fine. So what I will do, I will write Vr is equals to velocity, radial velocity by this flow, uniform flow is what? That will be equals to V infinity cos theta plus the radial component of velocity induced by this type of flow is what? Q by 2 pi r. Right? We have just seen. Just refer to this table. What I have given. Uniform velocity, radial component will be V infinity cos theta, and source flow radial component is Q by 2 pi r. Similarly, tangential component induced by the uniform velocity is what? Minus V infinity sin theta, and for the source flow it is 0. So same thing I will write here. Similarly,
Yes, sir.
V theta will be is equals to minus V infinity sin theta plus V theta for this is 0. Correct? So we have the velocity. Now, this is our first objective. What is our second objective? Our second objective is to find the stagnation point. Right? Our first objective was to find the velocity component. Second is the find the stagnation point. Right? And third will be the determination of Cp. And why Cp is very important, that we'll see. Now, uh, how to that? What is a stagnation point? A stagnation point in a flow is the point where your velocity vector is 0. Velocity vector is 0 means what? Your flow is totally, your velocity is 0 at that point. So there is no component of velocity. Your radial component will become equals to 0. Your theta component will become equals to 0. Now you consider this V theta. V theta is equals to 0 means what? My V infinity sin theta is equals to 0. Correct? V infinity cannot be 0. So sin theta only is 0. Sin theta 0 means what? Theta will be either 0 or pi. Correct? Now,
Yes, sir.
then this is the condition for, we have got the theta value. If we want V theta is equals to 0. Similarly, if Vr is equals to 0, then what will happen? Vr is equals to 0 means what? 0 will be equals to V infinity cos theta plus Q by 2 pi r. Okay. Now, you put any of these two values. I will put pi in cos theta. So 0 because we want radial component, the tangential component also 0. So just put this theta here. This will be equals to minus v infinity plus q by 2 pi r. So from this you will get r. R will be equals to q by 2 pi v infinity. Correct? What is this r? This is that r from origin where at this point you will have the zero velocity. Fine. So it basically tells us the location at which I am having the stagnation point. The stagnation point we will get at first of all I have to write the radial component, q by 2 pi v infinity, and next one is pi. Similarly, you can find for 0 also. There is no problem in that. Fine. This was our second objective. Okay. What is my third objective? No, I will extend it. First of all, there is one more concept in this that is important. That concept is sometime they will ask the width. What is width? Width of Rankine cycle they will ask. So not Rankine cycle, Rankine half body. Okay, there is a Rankine cycle also in thermodynamics. So the Rankine half body will be given as you are having the value of stream function for this Rankine half body. That is the summation of this stream function for the uniform flow and for this source flow. For uniform flow, the sign is equals to given as v infinity r sin theta. Okay, and for this it is given as q by 2 pi theta. You add these two, v infinity r sin theta plus q by 2 pi theta. Now at a stagnation point you will have theta is equals to pi, and my value of r we have determined by q by 2 pi v infinity. If you will enter these two values here, then you will get stream function as q by 2. This is called the width of Rankine half body. Okay, is it clear?
So if it is a Rankine of full body means psi is equal to q.
Yeah, correct. Full body. Why you want full body?
Rankine oval.
Okay, oval. Okay, you can. How you can tell? Correct.
Yes, sir.
Okay. Then next type of flow that is important. That one more type of flow is see in gate. I think the most important topic is the lifting flow over the cylinder. But anyway, before going on to that, we should have some basics. Then second flow what I will consider here is the non-lifting flow over circular cylinder. Right. See, non-linear flow over cylindrical, non-lifting flow, not non-linear, non-lifting flow over the circular cylinder is the summation of uniform flow, then doublet flow. Right. This combination of these two flow will give you the flow over cylinder, that is non-lifting flow. Right. Now for uniform flow, I know what is the stream function is given as V infinity r sin theta, and for this it is given as, just now we have seen, minus k sin theta by 2 pi r. So addition of these two will give you the flow over non-lifting flow over the cylinder. Fine. So if you will write it, you can write it for non-lifting flow over cylinder, V infinity r sin theta minus of k sin theta by 2 pi r. We can rearrange it and write, okay, what is k? I have not explained there. What is k? K is the Q into L. If you see this doublet flow, where is the doublet flow? This k is Q into L, and it is in such a way that these two are placed very close to each other. That means L tends to 0, not 0, it is tending to 0. They are coming closer to each other. Okay, that is a limiting situation. Fine. So basically, as of now, you consider K is Q into L. Q is the strength and L is the distance between them. Okay. Then we'll rearrange it. And we'll write it as, if you rearrange it, what we can take something common. What we can take common from here? We can take V infinity r sin theta, this full term as common. So this will become equals to 1 minus k by 2 pi V infinity r square into r square. Now this term is my r square, that is this r is the radius of cylinder. Over which flow is observed, over which you are observing the flow. So r square is given as k by 2 pi V infinity. Fine. Right. Now, so we can write this term as V infinity r sin theta 1 minus r square by r square. Okay. Now this is my sign in the radial coordinate system. This is not the Cartesian coordinate system. Fine. Now if I am having the value of stream function, I have told you we will be able to express the radial component of velocity by 1 by r del psi by del theta, and v theta, the tangential component, as minus of del dou psi by del r. If you will evaluate this thing for the given stream function, you will get radial component as v infinity cos theta into 1 minus r square by r square, and v theta as v infinity sin theta, actually it should be minus 1 plus r square by r square. So till now we have completed our first objective. Okay, first objective is what? I want to know what is my radial component of velocity and what is my tangential component of velocity. Fine. So our first objective is completed. Next objective is to determine the stagnation point. Right. So the second one is the stagnation point. Right. A stagnation point means what? I have told you radial component is equals to 0. Tangential components would be equals to 0. What is my radial component of velocity? V infinity cos theta 1 minus r square by r square. Fine. So if you observe, when your r is equals to the radius of the cylinder, in that case Vr is equals to 0. Fine. You just see, this is the cylinder we are observing. Now my r is what? This is the r. This is my origin. This is the r. When my r is equals to the capital R, which is what? Capital R is what? Capital R is the radius of cylinder under study or my system. Right. Now when you are at the surface of the cylinder, when you are at the surface of the cylinder, your radial component of velocity is 0. Right. Similarly, you will at this point you are having a radial component of velocity. You will be having a tangential component of velocity. What is that tangential component of velocity? Just see this. Then at r is equals to r, what is v theta? V theta is given as v in minus of v infinity sine theta 1 plus r square by r square. Okay. Now, when this small r will equals to capital R, then this expression will be v infinity sine theta. So my general expression for v theta at the surface of the cylinder is minus 2 v infinity sine theta. Correct? Now I want v theta to be 0. At what location my v theta is equals to 0? If you see this, for theta is equals to 0 and pi, we will be having v theta equals to 0. Correct? So if you consider this at this cylinder, at theta is equals to 0 and theta is equals to pi, these are 2 points where you will be having the stagnation point. What is the location of a stagnation point? R is equals to R and theta is equals to 0 or pi. So from this we will get 2 points, R0 and R pi. These are the 2 points of a stagnation. So I am having 0 velocity at this point, theta is equals to pi and theta equals to 0. Is it correct? At these 2 locations we will have the 0 velocity. Correct? So second objective we have completed. Fine. Up to this everything is clear.
Yes, sir.
Fine. So our second objective, we have met our second objective. What is our third? There is one third objective also. That is the determination of Cp, coefficient of pressure. I will come to the third objective. Third objective is Cp determination. Now, Cp I have told this is P minus P infinity by half rho v square, or you can write Q infinity. This is also expressed as 1 minus v by v infinity ka whole square. Right? This v is what? This v is the net velocity. Right? Now, if you at the surface of the cylinder, that is at r is equals to r, we are having Vr is equals to 0 and V theta is equals to minus of 2 V infinity sine theta. So if you see our net velocity, V will be equals to what? Root under of Vr square plus V theta square. We will insert this value here. So my Cp at the surface of the cylinder will be equals to 1 minus 2 V infinity sine theta divided by V infinity whole square. This will cancel. So my Cp will be equals to 1 minus 4 sine square theta. So this is the variation of Cp. How the Cp, if this is my cylinder, then the variation of Cp, if this is my origin, how the Cp varies along the, this is my theta. For a particular value of theta at the surface of cylinder, what is the value of Cp? Just insert the value of theta for different points on this cylinder. You will get the value of Cp. Correct? So there was a problem in some year, where I don't remember the year, where it is asked to find out the point where your pressure is equals to free stream pressure. You just tell me, when your pressure is equals to free stream pressure, what will Cp? Cp will be 0. What are the location of that point? If you will put Cp is equals to 0 here, that means 1 minus 4 sine square theta. So this implies you will get sine squared theta will be equals to 1 by 4, and your sine theta will be equals to plus minus half. And from the basic trigonometry, you can tell at what value of theta you will be having the sine theta as plus 1, plus half or minus half. Okay, this I will leave to you. Fine. Now, why Cp is important? See, for a body in flow, let's consider a cylinder in a flow. I am considering the non-lifting flow. Fine, the flow will be something like this. And this is the, I will just highlight it. This is my cylinder in the flow. Now this is the non-lifting flow we are considering. Now let's say if a body is kept inside a flow, then we will be having forces, right? Forces in the normal direction, and there will be some force in this direction also. That is, this is called drag, and this you are calling as lift. It is correct. This is my free stream velocity. This is the free stream velocity only. Then perpendicular component of force with respect to the your free stream flow is lift, and the parallel component of that force is called drag. Correct? By knowing the Cp, the center of pressure plot, not center of pressure, I'm sorry, the pressure coefficient plot, we will be able to tell what is Cn. This Cn will be equals to 0 to C 1 by C Cp in the lower half, Cp in the lower half minus Cp in the upper half dx. Right? What is the mean? And similarly for drag also, you will have 0 to C Cp in the front half, in the upper half. Okay, you can consider this upper half minus Cp in the lower half. Basically means pressure in this half and pressure in this half. This will be equals to. So this, if you will see this expression, or what is the interpretation of that? Well, if you are having the variation of Cp with x by c, okay, let's say there is some this type of variation I am getting. Not good. This type of variation you have got for some kind of body kept in. So the area under the curve is what? This is the area under the curve, right? So the area under curve, area under this Cp and x by c curve plot will give you the normal force, right? If you, let's say this is the Cp lower and this is the Cp in the upper part, in that case the lift will be equals to the area under this curve. Fine, you know, integration, by integration we get the area under the curve. So basically if Cpl minus Cpu, if you are doing, you are getting the area under this Cpl curve. First of all, you are determining area under this Cpl curve, Cpl by x by c curve, and you are minusing the area under this Cpu curve to get the Cn. Okay, is it clear? Fine. Fine. Now I will go to the lifting flow over a cylinder, the last topic of today's discussion. Now, lifting flow over cylinder. Now the lifting flow over cylinder is what? You add vorticity or the vortex flow in your non-lifting flow or a cylinder, right? This is what? This is a combination of our non-lifting flow is what? A combination of uniform flow plus doublet flow. And this is the vortex flow. So combination of this flow, these three flow will give you the lifting flow over cylinder. Fine. So so you can add the stream functions for these three type of flow, and you can derivate it. Psi, you can, if you know the psi, you can determine the Vr and V theta. I am directly writing the Vr. See, we know the Vr for this two type of flow, this non-lifting flow. What is that? That is V infinity cos theta 1 minus r square by r square. V theta for this non-lifting flow is what? Minus of V infinity sin theta into 1 plus r square by r square. Here I have told you r square is what? K by 2 pi V infinity, right? Now what we have added? We have added vortex flow to it. So for a vortex flow, you know, V theta is equals to minus tau by 2 pi r and Vr is equals to 0. Okay. So add 0 here, or here you add minus tau by 2 pi r. Now you are having the velocity component for the lifting flow over cylinder. Is it clear? Is it clear? Any doubt is there? Am I audible?
Yes, sir. No doubt.
No doubt, no?
Yes,
No.
sir. Yes, sir. Audible.
So I think up to till now everything is clear. We have completed our first objective, determination of VR and V theta. Now the second one. What is our second objective? Second objective is stagnation point. Right. Before determining the stagnation point, I will write the component of velocity. Now we want a stagnation point. That means what? This also should be equal to 0. This also should be equal to 0. How is it possible? You see, this VR, anyway, our radial velocity will be equal to 0 at r is equal to r. Fine. If you are having this small r is equal to this capital R, your radial component is going to be 0. Now, for this, you put this VR is equals to 0 condition in this. So this expression you can write V theta at r is equals to r is written as minus 2V infinity sine theta minus tau by 2 pi r. Correct? Now, this V theta should be equals to 0 to have the stagnation point. In that case, you can write sine theta is equals to minus tau by 4 pi r V infinity. Is it correct? That means you for a lifting flow, you know that my radial velocity is 0 at the surface of the cylinder, but your V theta should also be 0. This tangential component should also be 0. So at what point my tangential component will become 0? That theta you will get from this equation. Theta will be equals to sine inverse 4 pi r V infinity. From this equation, we can see two things. You see, we know that value of my theta for a sine theta, the maximum value of sine theta is 1. Correct? 1 or minus 1. If you go to the negative minimum value, that minus 1. In that case, we for this expression to be logical, if you want sine theta to be 1, that means what? Your tau should be, this will be equals to 4 pi r V infinity. In that case only you will be having sine theta as 1, or for being this expression logical, you should have tau less than 4 pi r V infinity. Is that correct? Correct. This expression to be logical, for r is equals to r, provided r is equals to r at the you are considering at the surface of the cylinder. Fine. In that case, these two conditions only arise. Either my strength of vortex should be equals to 4 pi r V infinity. In that case, that is the maximum value, or my strength of vortex should be less than 4 pi r V infinity. In that case, the value of this will be less than 1. You cannot have a value greater than 1. You cannot write sine theta is equals to 2. That is totally illogical. Correct? Sine theta lies between minus 1 to 1. That means my value, this value of tau will be always less than or equal to 4 pi r v infinity. Now, if it happens that my strength of vortex is greater than 4 pi r v infinity, in that case, my sine theta becomes greater than 1, which is totally illogical and which indicates us that you won't have any stagnation point on the surface of this cylinder. Is it clear? Up to this, everything is clear?
Yes, sir.
Yes, sir.
Fine. So,
Yes, sir.
this illogical expression indicates absence of root over cylinder. Correct. So where does the root lie? Root may lie either inside of this cylinder, which is not possible, it's a solid body, or it is outside of the cylinder, but not on the surface of the cylinder. But for this course, we are interested in this logical part of it, that on the surface of cylinder where it is lying. Okay. So we'll consider this case when strength of vortex is either less than or equal to 4 pi r v infinity. Now you see, we are having expression of theta as sine inverse minus tau by 4 pi r v infinity. Correct? And we are interested in this expression. Now, in this also there are two conditions. The first one is if my tau is equal to 4 pi r v infinity. Other one is this is less than the 4 pi r v infinity. First of all, consider this case. If this is the case, then you will have sine theta is equal to sine inverse minus of 1, and that theta will be equal to 270 degree. Right? And from this expression, you can tell that sine theta is negative only in third quadrant or fourth quadrant. Correct? My theta is going to be negative. My sine theta is going to be negative. That means what? My roots lies either in third quadrant or in fourth quadrant. Correct? So, to have a single stagnation point, you should have tau strength of vortex should be equal to the 4 pi r v infinity. In this case, you will be having one stagnation point only. Correct? That is at theta is equal to 270. Now, if you are dealing with this case, in that case, you will be having two roots, or you can tell two stagnation points. One stagnation point will be in third quadrant and one stagnation point will be in the fourth quadrant. Correct? Is it clear? Yes or no?
Yes, sir.
Fine. So with this, I will complete the revision session with one question. I will give you one question. Please try to solve it. If you have understood this revision, you should be able to solve this. That question is, for a flow of a cylinder CL, the coefficient of lift is given by 5. Calculate negative peak pressure coefficient. Right? You solve this question and you can send it in the group. Fine, so you can send the solution in the group. Anybody is having any doubt